this talk. So I guess people here in the auditorium already know about Aamir and those who are online. So Aamir was a former PhD student from physics department. He completed PhD in 2017.
Yeah.
And you are working on bilayer graphene systems,
Yeah.
electron transport. So after PhD, completing PhD, he moved to Barcelona, Spain, as CFO, looking into thermal properties of graphene systems.
Yeah.
And after that, he moved to University of Technology at Chalmers, where he's working for the last 3 years, looking into a new topic of quantum thermodynamics. So today he will be talking about thermally driven quantum refrigerators using superconducting qubits. So, what are you doing?
Thanks, Vibhor, for the introduction. It's my great pleasure to come back to ISC and thank the organizers, including Arindam Da, who's unfortunately not able to attend right now, for hosting me. So this is the second of my talk in this Quant Talk series, and I'm back to present some of my more recent results. So this is, some of you have already seen the title. I would like to break it down about what it is about. So it's about a quantum refrigerator, which means that the refrigerator is made of qubits. It is driven by heat bath, as quantum thermal machines, a heat engine or refrigerator should be. What is quite special about this system is that we have to engineer a three-body interaction for it to work, as you'll see why it's important. It does a very important task of cooling a qubit to a ground state. And a very salient feature of this, which is very well received in the community, is that this is an autonomous quantum thermal machine, which means that it does its job autonomously without having any external control or feedback to manipulate the heat in the system. This work has come already in archive, so you can also look up the preprint. And this is in the context of quantum thermodynamics. So thermodynamics, as you would recall, is can be thought of in this paradigm, where you have a system, a working medium, in contact with a cold bath and the hot bath, and it could be either doing some work or extracting work, or it could be using up work to do some task. So we can think of what would be interesting quantum version of that. So that would be with this system uh, replaced with quantum systems. So the thermal machine is made of quantum systems, and this is in contact with the hot bath and the cold bath. So these quantum systems, of course, have the discrete energy levels, but you could also have some interesting quantum resources, such as superposition, entanglement, or quantum noise, even that could be driving this machine. So that would be how a quantum thermal machine would look like. And in the community of quantum thermodynamics, what we have been thinking about or asking a question for a long time is if there is any quantum advantage in thermodynamics, which means that's just like you have some advantage in quantum computation, a quantum advantage. Could you have such an advantage if you had scaled down everything to quantum systems? So questions such as, can you beat any classical machine in terms of power output, charging speed, or precision? But there's another aspect to this, that even if we figure this out, how would you deploy that in applications? What kind of settings would you use it in? And this is where we thought of using quantum thermodynamics to do an important task of qubit reset. So qubit reset is actually one of the DiVincenzo's criteria for quantum computing. In order to do quantum computing, you need to have very good high purity states, especially the ground state. So you want to be able to initialize to the ground state. And it often happens with qubits, especially superconducting qubits, which form the leading platform for quantum computing, is that the qubits are always constantly getting excited by the environment. So even if you let it decay down to the ground state by default, there's always some disturbance from the environment, such that in a steady state, your ground state population is about 97 to 99%. And that is in the stochastic sense, so that if you took a qubit, did about 100 measurements, you would find that 99 times it's actually in the ground state, but one time it's in the excited state. And that is actually that will lead to significant error in quantum computing. So it's one of the important tasks to bring it to ground state properly. And there, the key metrics is what exactly is that population and how fast can you do that for computing. So to this end, in the field, there are a few protocols followed to do this. So one of them is called active reset, where you take the qubit and you actually measure it real time. If it's in the excited state, you quickly flip it with 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 another gate over here. Let me get the pointer. Excuse me, I just flipped it. I clicked the wrong button here. Right, and I wanted to get the laser pointer. Yes, excuse me for that. So yeah, that is the approach in active reset where you do that flipping real time. And the other approach is to do unconditional reset where you have sort of a switch, which if you turn on, you connect the qubit momentarily to a very cold bath, which will sort of suck out its entropy and bring the qubit to ground state. Now, these are actually quite expensive in terms of resources. You need to have a good some drive protocols and various coherent drives to be able to execute that. What we asked is that whether we could do this useful task with a quantum thermal machine using only heat baths, which are typically abundant in nature. You don't really need a coherent light to drive that. So for this, we look at something called absorption refrigerators in the macroscopic world. So these are useful quantum thermal machines that cool an object by using only heat from a hot bath, not thermodynamic work. Because refrigeration requires a source of free energy. In some refrigerators, we do that using we use thermodynamic work to do that. But you could also use a natural flow of heat as a source of free energy. So the first actually usable a system that could for an absorption refrigerator was actually proposed by Einstein and his student Szilard back in 1930. And the same idea has actually been used even now in industrial settings, where in some industry you will have a lot of heat generation, and you could connect such an absorption refrigerator to use that excess heat and do something useful in the industry itself. So that's a more energy efficient way of running the facility. So one bad feature of a absorption refrigerator is that it has a slight low coefficient of performance because it operates quite in an irreversible condition. So it's far from a Carnot efficiency requirement. However, it has high utility, so you use excess waste heat for something useful. Thermal baths, which is driving it, are always abundant in nature, and it's also autonomous, which means that you don't need any external control to drive it. So we now a quantum version of this has been proposed a few years back. So that consists of three quantum systems, and each of them is connected to a bath. And here, the way it works is that you have what we call a work reservoir, because this is sort of the substitute of the work, but it's a bath. And that there you have a heat flow from that work reservoir to a system which is the heat acceptor, and that heat flow drives the refrigeration from a cold bath, the blue one, back to the heat acceptor. So in that process, we cooled on this blue reservoir. So this has been realized with trapped ions, but that was a proof of principle idea, which did not do anything useful. It just showed that you could do some refrigeration. There was a proposal with superconducting circuits. And what we did was we came up with a different proposal, but we implemented that to do something useful, which is a qubit reset.
So I was okay. The Q is the highest temperature.
That's right.
So okay.
Right. So TC is the coldest, TH is intermediate, and TW is the highest. So you have the highest to the intermediate flow, which is natural. And as a result, you have the coldest one losing its heat, and that goes to the intermediate temperature. So to implement a qubit reset with quantum absorption refrigerator, this would be the rough scheme. So we have three qubits over here, two of them which are auxiliary qubit, which means that they are something we engineer for this purpose. They are connected to controlled reservoirs, and these reservoirs, along with the qubits, form the quantum thermal machine, whose job is to cool down the target qubit, the green one, which could be connected to this uncontrolled reservoir, which is what basically is constantly exciting it, and in steady state, keeping it slightly excited above the ground state. So in order for this to work, we need a three-body interaction between these three qubits. So this is written in the second quantization language. So an H and T means that these are the annihilation operator for the red qubit and the green qubit, and C dagger is the creation operator in the blue qubit. So what this means basically is that in the target qubit, when it is excited, then nothing really happens. But when you also have the red qubit excited and the resonance condition is matched, which means that the sum of this transition energy of the red and green equals that of blue, what happens because of this interaction term is that these two excitation will basically be transferred into the blue one. So this Hamiltonian drives that process. And once we have that excitation in the blue one, this is connected to a very cold bath, the TC, and that excitation will be lost easily into the blue bath. So this is and in the process, what has happened is that the green one now is in the ground state. So it's no longer excited, and that's what the job was. So in order for the scheme to work, there are two important ingredients. So one of them is control baths. We have to be able to control this bath because to get the red one excited, we are using a heat bath. So that should be hot enough. And the blue one should be cold enough so that it absorbs that excitation energy from the blue one. As well as we have to also engineer the three-body interaction. So now I'll show you how this will be implemented with superconducting circuits. And I would give a brief primer about superconducting circuits for maybe a diverse audience here. So it's something which has been growing since about 2000. And over here, you can see what the general scheme of this is. So why superconducting? Why this platform is a leading platform in quantum computing or similar light matter interaction is because of the superconductivity, which drastically reduces energy losses. So you typically have this energy as electromagnetic energy, but if you don't have any resistance, then you can keep it quite long. You can engineer artificial atoms with tailored energy spectra very easily in this platform. And you can also engineer strong light matter interactions, which are actually quite otherwise challenging in natural systems where you have a natural atom, say rubidium or cesium, connected to a waveguide which will supply the light for that interaction. And in this, over here, you can also engineer the coupling efficiency between a waveguide and an atom to reach something close to 99%. So it's a very easy system to engineer. So some of the building blocks over here are, for example, waveguides. So this is the waveguide which basically channelizes the light energy along the circuit. You have cavities, which basically traps the light inside some of these waveguides, which is where it will interact strongly with the atom. And then that artificial atom, which for example could be a transmon, is basically a circuit with a capacitor and a Josephson junction shown in this schematic here. So I'll go a little bit more into what transmon is like. So it basically originates from a standard LC oscillator. So if you have a L and C and you connect them together, it will be basically an oscillator in two conjugate variables. So one of them is the charge in the capacitor, which could come down to the Cooper pairs in a superconducting circuit, and the superconducting phase of the superconducting condensate in the circuit. So these two form the variables of this oscillator, and when you quantize it, you basically have discrete energy levels which are equispaced. Now, to if we can convert this oscillator into an anharmonic oscillator, if we use a Josephson junction, where this quadratic term in the superconducting phase is replaced with a cosine function. And because of this cosine function, this is not harmonic anymore, but you can still quantize it to this discrete energy levels, and you will find that they are no longer equispaced. So now if you focus on the first two levels of this oscillator, or sorry, for this transmon, you find that the transition energy is different for the next two levels. And you can therefore limit your electromagnetic excitation to that particular frequency so that you're only talking within that within that subspace of the Fock space, which we also call the computational subspace, because that's what's used in quantum computing efforts. So now when we quantize this particular Hamiltonian, it's basically an approximation to the harmonic oscillator with some fourth order terms. And as a result, the Hamiltonian looks like that of a harmonic oscillator with some anharmonic terms, which is given by this higher order term, B dagger, B dagger, BB. And and also we from the electronic values such as the inductance and capacitance, we would know what is the frequency and what would be the enharmonicity. So it's a very well understood system. So now let's say the in this business we often couple the qubit to a resonator, and this is what a qubit would look like. For example, this is one of those qubit designs which are popular. It's also called XMON. So over here, it's made of this plus symbol, and this forms one of the plate of that capacitor of the transmon. So that's the blue one over here, whereas there's this whole metallic plate surrounding it, which we also call the ground plane. It's actually the other plate of the capacitor. And these are shunted by Josephson junction, which here in this picture is over here. It's a small structure which zoomed up looks like this. So it's a Josephson junction with two aluminum separated by an insulator, which is aluminum oxide in this case. So this together form that transmon, and it's coupled to this resonator, which basically has its own discrete energy levels. We can think of that as an oscillator. Uh, because it is cut off on both ends. As a result, it will have that discrete energy levels. On the other hand, and after that is connected to this waveguide, which and the waveguide basically connects to the input and output fields to which we can connect our instrument. So this basically hosts all frequencies, but the resonator has a fixed frequency because you form that standing wave inside the resonator, and the qubit has its own frequency. So I won't go much into this, but this is a scheme used to read out the state of the qubit, whether it's in the ground state or the excited state in that two-level computational subspace I mentioned earlier. The way it's done is that we use the waveguide to read out the frequency of the resonator, and the frequency of the resonator depends upon the state of the qubit. So experimentally, it looks like this. So the blue one is when the qubit is in the ground state, and the red one is when it's in the excited state. You see that in the excited state, the frequency of the resonator has shifted, and that's because of the dispersive coupling between that. So this is how qubit readouts are done. There's another scheme which is important and very relevant to my talk is that instead of connecting the resonator or having the waveguide and the qubit basically disconnected by the resonator, we directly connect the waveguide to the qubit. And this waveguide can host all ranges of frequency. So it does not have a specific frequency. And as a result, you can send and study the qubit through this waveguide itself. Or the waveguide could, for example, be used as a heat bath, which is what I would like to do. So we use this waveguide as heat bath as follows. So the waveguide would interact with the qubit as long as you have the modes in the waveguide which have the same frequency as that of the qubit. So what we could do in order to connect the qubit to a thermal bath, we would populate this waveguide with thermal radiation or black body radiation. Now, when you have black body radiation, you have these photons, and those photons of the right energy, the frequency of the qubit, they will interact with it and they will thermalize because it's black body radiation. However, instead of doing that, what we do, what matters, so one important thing is that what really matters to the qubit is that you have that black body radiation only around the frequency of the qubit because that is where it interacts. You really don't need the full spectrum that we get from a natural black body source. So what we do in the lab is that we have an artificial noise source which generates a a radiation with a flat white noise spectrum around the frequency of the qubit, and then we populate the waveguide with that. So what it allows us is that we can control the magnitude of that noise, and as a result, we can control the temperature of that bath very easily in the lab. So these basically have ohmic spectral density. We can also synthesize other kinds of spectral density if we wanted. And in a previous work, we showed that we can use the qubit to do a thermometry of the radiation that we create in the waveguide, which we call quasi-thermal because it's not full spectrum, it's only within a narrow bandwidth. And we see that there's a very good agreement between what we synthesize artificially with natural thermal baths, which we did by just heating up the locally in our cryostat. So this is how we realize heat baths in our setup for it to interact with the qubits. Now I'll show you. Yeah.
The temperature of the free is qubit is predominantly coupled to
It's connected to the thermal radiation, which 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 need not be the electronic temperature either. Because from my understanding, of course, the phonons and electrons decouple at those temperatures. Uh, but but even the thermal radiation could have a much higher temperature than the electrons, because again because they are not very well thermalized. On the Having said that, that's right. So we saw this agreement usually at higher temperatures. At lower temperatures, because when we heat the cryostat, we know that the temperatures really match with electron and phonon at higher temperatures where we saw that agreement, but they deviated at much lower temperatures, where we know that our phonon temperature was not really matching that thermal radiation. So now I'll come to the three-body interaction, which is the second ingredient I mentioned. And for this, we use the Josephson junction, which allows us to mix modes. So what that means is when we have a Josephson junction in the quantum circuit, it contributes its own energy, which is Ej into cos phi j. Phi j is the phase difference across the junction. And it turns out that you can really separate the linear and the nonlinear part in a quantum circuit. The linear part itself has all its modes, which are designated by A dagger, B dagger. But with the help of the Josephson junction, you basically mix all of them and put them inside a cosine function, which means that now you also have fourth order terms, and that allows you to mix A and B, which otherwise were not mixing up. They were two different modes with their different frequencies. But with the help of Josephson junction, we combine them together and we can have mixed terms. So right now, between two bodies, we will of course see A, B mixed up. Now I'll show you that we can have that for three body as well. So this is where the quantum absorption refrigerator comes. So this is the scheme where we have two of the auxiliary qubits connected to a target qubit over here with a three-body interaction. The way it's done is that we have this G next neighbor coupling, G and G prime, and that allows the three-body interaction in such a way that now we have a annihilation of the red qubit and the green qubit, which gives a double excitation in the blue qubit, going from ground state to the second excited state. And that looks like A1, A2 dagger, A2 dagger, A3, which in the quantum circuit, this appears like this. So we have these three qubits where the green one is the target, and we have the Josephson junction in each of them, which allows the mixing, which puts all of these modes inside a cosine, and that leads to this kind of term. Basically it's a four-body term, but two of them are for the same system. That's how we basically achieve that three-body interaction. And what is important is that this resonance condition has to be valid for this process to occur. Otherwise, energy won't be conserved. And for this reason, we made sure that we have at least one of those qubits which is tunable. So over here, we have the blue qubit connected to a squid, a double Josephson junction, which allows us to tune the frequency of that qubit and achieve that resonance condition. So the frequencies are typically omega 1 about all the transmons have similar frequencies, which we use typically in superconducting qubits. And we also, the one of them which matters also is the anharmonicity, which is about 200 megahertz. So this is just giving a snapshot of how we put that device inside a cryostat. So this is where the device would be at about 9 millikelvin, connected to a circulator, which basically separates. So this is for the experts. It separates the input and output lines. The input line is where we have a bunch of resistors, attenuators, which dampens the thermal radiation at each stage. And the output line has the amplifier, which basically amplifies the signal coming from the device. This is kept inside a dilution refrigerator at the bottom over here. So now I'll show you a proof of the three-body interaction. So to do this, we have this pulse scheme where we drive some of these qubits and we read out some of the qubits. So the way it works over here is this, as follows. We basically first initialize the target qubit with a pi pulse, which means that you take all the population from the ground state to the excited state. And this is what we want to reset. We want to bring it back to the ground state. So to do that, right after doing that, we start driving the qubit 1 with a coherent drive, which means that with a monotone, we basically drive a little bit of population from the ground state to the excited state. And now that you have these populations in both the Q1 and Q3, if our three-body interaction is valid, what would happen is that both of them will be exchanged with the blue qubit, and that will get excited. So after having done that, we do the readout. Actually, I have the steps here. So excite Q3, drive Q1, and then we measure Q3 again. And we would do that for various different frequencies of qubit too, because we need to hit the resonance condition for this process to occur. So this is the experimental data. In the x-axis, I'm driving the drive frequency of qubit 1, which is basically trying to drive the qubit 1 towards its excited state. In the vertical axis, I am tuning the frequency of the qubit 2, so basically tuning across the resonance condition. And I see that when both the frequencies match up with the resonance condition, I see a sudden change in the state of the qubit 3. So note that what I was varying was qubit 1 frequency and qubit 2 frequency, and I see a change in the third qubit. So that's basically how we connect this three qubits. We see when we hit the resonance condition, the state of the qubit, which was originally 1, because I excited it in the beginning, goes towards the ground state. So that is showing that we have the three-body interaction. All right, so now we can park our frequencies at the right spot at the resonance condition. And now we look at the state of the qubit as we increase the strength of our qubit 1 excitation, which means that we make it closer and closer to a fully excited state. We see that when we increase the drive rate, as we keep on increasing, we go from decay of the qubit 3, which looks like natural relaxation. So it naturally relaxes automatically with a lifetime of about 17 microseconds if you don't do anything. But when we start driving the qubit 1, we see that it relaxes much faster, and about 500 nanoseconds, it has already come very close to the ground state. So this is showing the three-body interaction with coherent drives. Now I'll show you what happens when we start using the thermal baths.
Okay.
Yes, correct. Yeah, it's a bit difficult to simulate three-body interactions because with all the Stark shifts and things like that. The moment we apply a qubit 1, we have a bit of Stark shift around the other. So this is why our fittings are not to the point. It's just mainly because of the complexity of the device. So this is the part where we come to use thermal baths to drive the refrigeration. And the scheme begins again with this. So we excite qubit 3 again. And now we elevate the temperature of the hot bath, which is connected to qubit 1. So that means that we make the qubit 1 more and more populated. And now since both of them are simultaneously populated, we expect that it will exchange its excitation for a double excitation in the blue qubit. And we make sure that this is connected to a cold bath. So there's only very few number of uh, thermal photons. So Nc and Nh represent the photon number in the baths. So there's only very few photons in the cold bath. So then this excitation will be lost into the qubit 2 or into the bath of the qubit 2. So this is that experimental results. So over here, we begin with, let's say, with zero number of photons, close to zero number of photons in the hot bath. And we see that qubit 3 decays at its own default relaxation rate, which is about 17 microseconds, as I mentioned. But as we start heating up, so now we are actually heating up a qubit, what happens is that it increases the rate at which qubit 3, the target qubit, starts decaying. So we see ultimately when we go to high enough number of photons in the hot bath, which is about 22, 21, we see that it decays almost by a rate which is now about 70 times faster. And now you see what is interesting is that all of this over time goes below these two dashed lines, the green and the blue. So the green line is basically where we find the qubit 3 by default. If we don't do anything, we find that as I said, the constant excitation by the environment leaves it at a level which is about 0.028. And now let's say it goes below that. So it's cooling definitely. And then the blue line shows the blue dashed line is when if it is connected to the coldest bath around, which happens to be the cold bath of this qubit 2. If it were connected to that, that is where that population would settle. But we see that it actually goes about 2 orders of magnitude lower than those lines, which means that it's cooling much below all the baths which is available in the circuit. So the steady state population is close to about 0.0005. And if I convert that to an effective temperature, that's about 23.5 millikelvin. And the coldest bath around is about 45 millikelvin. So this is the reset time we have over here to reach this is about 1.6 microsecond. And one important point to note is that this is autonomous refrigeration, which means that you just turn on these baths and it automatically cools down. You don't really have to send any control drives or have any feedback. So it would be a good point to compare this with the state of the art to do qubit reset. And if we do that, we find that in 1.6 microsecond, we go as low as about 0.2%. So that falls very close to the state of the art. And if we wait longer for about, let's say about 20 microseconds, we really go off the chart here. So it's much lower population than what is achieved with all the protocols, which is used in the field. However, you will have to wait much longer. So it's not very applicable, but it shows that in one metric, it exceeds all the other state of the art. So this is where I come to the summary and outlook. So what we showed here is a demonstration of a useful and fully autonomous quantum thermal machine. Its performance is competitive with the state of the art. And an interesting outlook would be about how it could be used. So what we did in our experiment is that we had tunable um, thermal baths because we were basically creating this thermal bath with artificial noise. But what one could do also is that connect it to actual plates in the dilution refrigerator. So in the dilution refrigerator, we already have some stages with fixed temperatures, 3 Kelvin, 700 millikelvin, 100 millikelvin. And we can connect all this waveguides directly to that bath, to this plate, and let it drive that qubit reset autonomously. We just need a switch to turn that on and off. You should turn it off when you want to do computation with the qubit, but now you have naturally abundant sources to do the qubit reset. So what also a broader outlook is that now with this quantum thermal machine operating and doing something useful, we show that circuit QED and with the help of this thermal waveguides could be a very good way, a very good platform to study quantum thermodynamics. So this work was done in Chalmers University of Technology in the lab of 22Q lab, and we had theory support from the group of Nicole Junger Halpern in Maryland. And maybe I'll tell you a bit about our lab. So our lab, what I showed was quantum thermodynamics. It actually falls in a very broad spectrum of research that we do in the lab with superconducting circuits. So it goes from fundamental and what I showed was quantum thermodynamics, but we also do somewhere in the middle applied with quantum computing with bosonic modes, and even do more applied research where we develop microwave filters and microwave switches. Some of that actually have started going into a product in a spin-off. So it's a very broad spectrum, and we are constantly looking for people to do this research with us. So if anybody is interested, we are still hiring. We are looking for more PhD students and 3 postdocs, especially to do some fabrication. As you see that we have very cutting edge nanofabrication laboratory where we design these devices, and we would like to have more people making these devices. All right, thank you. Yeah, so here in Q3, I don't show anything, but there's actually, as I showed in a schematic before, it's connected to an uncontrolled reservoir. I can't control that bath. I'm just trying to basically beat it and bring down the temperature of the qubit. So I'm not controlling it. I don't show it in my pulse diagram. I show only the hot and the cold, which I control. And in the case of qubit 2, for this particular result I'm showing in this slide, I did not do anything for the bath of qubit 2. So I let it be. And it turns out that by default is about 45 millikelvin. That's the temperature of our cryostat can achieve. On the other hand, on the hot bath connected to the red qubit, there I'm sending artificial noise to raise the temperature of the radiation photons, of the radiation in the waveguide. I do also in the case of the blue one, where I send radiation over there so that I raise the temperature of the cold bath and see how things change. And you can easily guess that what would happen is it won't go to the lowest temperature or lowest population here, because now this qubit 2 is also slightly populated. So it has less space for receiving that excitation from the other two qubits. So I don't show that experimental data, but the idea was to increase the cold bath temperature as well. In this case, I want it to be least, so that I can show you what is the least target population I reach. Yes, so in this experiment, I do pulse it, but you can also think about this as a way for me to control the duration. I'm doing this only to change the duration, and I see a dynamic curve. On the other hand, I don't really need to do that. As I said later on, I could connect to a source of hot bath. I could let it all be on all the time, and that would autonomously, which means that it happens automatically without me trying to control anything. So I do have control over here, but only to get my experimental plots.
So will you call like a ice cube?
So the macroscopic version of this, as I mentioned earlier, used in industries, you can connect this refrigerator to something which is hot, and that can, for example, run the air conditioner in a room. That I would call autonomous. Again, it's a concept thing. Of course, there are a lot. So when we have this, of course, this dilution refrigerator, which is taking up a lot of energy, right, to drive it. But it's that particular feature which we call autonomous.
Higher accepted state, then what will happen? Like you are assuming that it will go to the fast accepted state, and you are tuning your qubit to accordingly, and you are like trying to bring the qubits three to be to the ground state. So what if it goes to some higher accepted state?
That's a good question. So we expect that there is some population even in the higher state as well, but it becomes exponentially lesser because you can think about Boltzmann factor, exponential to the power minus e by kBt. So if you assume that there's a constant t, when you go to higher level, you will see that it becomes even less. However, by the time I come to the baseline, I do find that it's comparable to that at the higher state. And what would happen in that case is that this process is only driving the refrigeration or basically evacuating the first excited state. But now you will have some decay from the second excited state to the first excited state. So after some period of time, you will find that all the higher states are also getting evacuated.
Questions online? So I read the question. First one is, can we use a linear resonator instead of qubit cube? Would it give any different?
Yeah, that's a good question. I think it is possible to engineer that, but you could extend that question and ask, okay, can you have three resonators to work? And the answer is that not really, because you need at least one Josephson junction. So Josephson junction is the way we actually engineer the three-body interaction. So it's achievable with if one of them is a resonator, and maybe even if two of them are resonators, but not all three of them can be resonators without a Josephson junction.
At least one.
Yes.
Second question is, what was the usage of phase flip gate post measurement? I guess it is on second slide. I think it's about the activity center.
Yeah. So yeah. So as I said, if your ground state population is about 99%, it means that if you do a measurement about 100 times, you will find that one time it's in the excited state. And in order to reduce all these errors, you don't even want that. So what you do is that real time, you do that measurement, and you have an internal register which is taking into account what that result is. The moment you find excited state, depending upon the state of that qubit you found, you use that information from the register and apply the Z NOT gate to bring it back to the excited ground state. And that way you will have a better ground state by the time it comes out of this process. Yes. No, the T1. No, actually, the relaxation time this of the qubit 3 does not matter. No, the qubit 3 could be actually anything. Yeah, it could have any default. In fact, even the reset population does not matter on what is that bath it is connected to. So it could have had a higher temperature, but this qubit will ultimately, in steady state, will come down to the same temperature. Time for? Oh, yes, yes. So yes, so part of the optimizing this circuit was to make sure what are those coupling rates of the qubit 2 to its path and qubit 1 to its path, and the different interaction coupling rates between qubit 1, qubit 2, qubit 3. So all these energy scales have to be optimized to have the best reset time in population.
There's no other question. Let's thank Aamir once again for the wonderful talk.
Thank you.
So Aamir, we have a small momentum.